Now we're going to learn how to find the uncertainty of a calculated quantity. For example, if you measure the distance something travels and how long it took to travel that distance, you can divide those two quantities together to find velocity. Well, how do you know the uncertainty of velocity? We could know the uncertainty of the time by the method for figuring out uncertainty for a measured number. And we could figure out the uncertainty for distance similarly. But how do you find the uncertainty of velocity, which was not measured but calculated? So the uncertainty of a calculation is all based off of the operation that you used to get that quantity. So there's different rules. There's one for sum and difference, one for product and quotient, fancy words for multiplication and division. There's one for the nth power, so if you ever want to do something to the power, or nth root, or average. Let's say we have an object that's rolling along at two different segments of track, and we've measured those two different segments, one to be 0.53 meters plus or minus 0.03 meters, and the other one was 0.32 plus or minus 0.01 meters. Now, if we want to find the total distance traveled for this object, we'd obviously have to add these two together. Now, if we want to know the uncertainty of the final result, we need to look at what the maximum possible answer could be and the minimum possible answer could be. So the maximum possible answer would be if we added 0.03 to this number and added 0.01 to that number, right? We'd get the maximum possible answer of this number here, 0.89 meters. Okay, and then we're going to also find the minimum and the actual amount. So the actual amount is just with the numbers itself, 0.53 plus 0.32, and then the minimum would be where you subtract the uncertainties from both. And so this is the range of possibilities given the uncertainties of the two measured values. Now if we look at that, this is the number we're actually going to calculate, and we're going to state this is the value, right? And so we say, but it's possible that it could go all the way up to 0.89 and all the way down to 0.14 or 0.81. So what that means is there's a difference of 0.04 variance, either up or down, plus or minus. Okay, so this is interesting. So how can we get that information without going through this whole process? Well, if this guy's uncertainty is 0.03, this guy's uncertainty is 0.01, you add those two together, you got 0.04. So here's the rule. If you have a number that you're going to calculate by adding two numbers, this is a plus b, or a minus b, if you're subtracting two numbers, it's the same rule. Then this is what you do to find the uncertainty of that value. So y is the new calculated value. In this case, it would be the total track. Delta y is the uncertainty in this new calculated value. Delta a is the uncertainty of a, the first value. This would be 0.56 in our example. Delta b is the uncertainty of b, which is the second number, and our example is 0.32, so the uncertainty for delta b is 0.01. Okay, so this right here is a rule. You'll find it in your pink packet, and you can use it to calculate the uncertainty of any calculated quantity where the operation performed to get that number was either addition or subtraction. So a couple of quick examples to show, right? This is how you would write it out. The one that we just did. Okay, so here's the answer. You would say the answer is 0.85 plus or minus 0.04, right? That's the value we got. But even if we subtracted these two values, right, 0.53 minus 0.32, which gives us 0.21, the total uncertainty still goes up. You always add the uncertainty together. So it also has an uncertainty of plus or minus 0.04. Before we can figure out how to calculate the uncertainty of other types of calculated quantities with other operators such as multiplication and division, we need to first discuss what a percent uncertainty is. So to talk about that, let's say we're trying to measure the height of a dinosaur. Now, we get our ruler out and we find out, this shrimpy little guy is 12 inches big, or 12 inches tall. Now, we have to use our knowledge about how to figure out the uncertainty of this measured quantity. Let's say we did that, we did it correctly, and we figured out the uncertainty is about 12 inches as well. Okay, so what does that tell us? Well, what we're going to do is we're going to create this new quantity, calculate this new quantity of delta h over h, or in other words, the uncertainty of the value divided by the value. So if we calculate that quantity, it would be 12 over 12, which is obviously equal to 1. what does this new quantity mean? When we take the uncertainty of a value and divide it by the value, this 1 here means we are 100% unsure about how tall this dinosaur is. A height of 12 inches and an uncertainty of 12 inches just really goes to show I know nothing about it, right? Well, let's say my uncertainty was a little bit better. Let's say instead my uncertainty was only 6 inches. We do this calculation again, we get 1/2. What does this mean? That means we're 50% uncertain about how high this dinosaur is. Percent uncertainty is simply the ratio of the uncertainty over the actual value itself, and it represents a percentage of the original amount, the actual value of how much plus or minus we are uncertain. Let's now learn how to calculate the uncertainty of a number that was calculated by use of either the product or quotient. Product is a fancy word for multiplication, quotient is a fancy word for division. So let's say I wanted to measure how wide this building here is. Okay, I don't have a giant meter stick, so instead I'm going to jump in my car and I'm going to time how long it takes me to drive from one end to the other, and with that information I should be able to calculate the length or width of this building. So let's figure out some percent uncertainties while we go, since we just learned that. So the percent uncertainty for the velocity in this case would be about 20% uncertain, which is pretty bad. Then let's say I measure the time to be about 4 seconds with a ½ second uncertainty. That leaves us with a percent uncertainty for our time of 12.5% uncertainty as well. Now we're going to do the same analysis we did with the sum and the difference, where we're going to find the maximum value possible by, again, combining whatever number I could have here by really adding these two and finding the product, and that would give us the maximum value. And we're going to find the actual value, and we're going to find the most minimum value we can have. Now let's again look at the difference to see how much this actual value can vary up and how much it can vary down. So we can see up, there's a difference of 21, plus 21 going up, and going down, negative 18. This is kind of annoying. The product and quotient doesn't actually have a single amount that it goes both up and down. However, let's just find the average change either up or down. So if we average these two values, 21 and 18, we add them up, we divide by 2, we get an average of plus or minus 19.5. So we'll just say, in general, for simplicity's sake, it could go up all the way to 19.5 and it could go down all the way 19.5. So that number, can we, like we did before, can we get 19.5 from this uncertainty and that uncertainty? 3 1/2. I'm not sure how we could combine these in any way, actually, in order to get this quantity here. Where did this quantity come from? Well, let's find out the final values percent uncertainty. This is the uncertainty of the final product. The actual product is 60. 15, right, meters per second times 4 seconds is 60 meters, with an uncertainty of plus or minus 19.5. Let's find out its percent uncertainty. So 19.5 over 60 is 0.325 or 32.5%. With the percent uncertainties, notice 20%, 12.5%. If you add the percent uncertainties together, you will get the percent uncertainty of the final value. This is useful. We can make a rule from this. So our rule for both product and quotient is as follows. If we have a quantity y that was calculated by either multiplying two values together or dividing two values together, they're trying to show both rules in one, then what you do is you take the uncertainty of the final value. This is the uncertainty of the final value, but delta y over y, this would be percent uncertainty, right? So it says the percent uncertainty of the final value will equal the percent uncertainty of A plus the percent uncertainty of B if you are multiplying them together. And if you divide by a number, then you add the percent uncertainty of that value as well. So the percent uncertainty of the final calculated quantity will be the sum of all the percent uncertainties of all the values either being multiplied or divided. This is also found on your pink sheet. Let's go over an example of finding the uncertainty from a product, just so you can get a better idea of how to use this rule because this is one of the more confusing rules. Let's say we are looking at a rock that has a density of 1.6 plus or minus 0.1 grams per cubic centimeter. And the rock has a mass of 27 plus or minus 3 grams. What is the volume of the rock? So if we want to find this, we're going to have to use the formula that density rho, okay, density rho is the symbol for density, times the mass will equal your volume. So if we want to do this, we just got to plug in our numbers and find the actual final result. 27 times 1.6, and we get 43.2 cubic centimeters. Now, if we want to find the uncertainty of this value, we've got to use our rule that we had. Okay. Now, notice, just for emphasis, notice this is a times b divided by c. I'm multiplying two values, a times b, but notice in my equation, I'm not dividing by anything. So I'm going to do a times b, and you know what? I just don't need the c value since I'm not dividing. I'm going to get rid of that part of the equation. I don't need it. The equation still works just fine. So a times b, what do? I look at the percent uncertainty for the final value will equal the percent uncertainty of the two individual values. So let's see here. In this case, the final value is v, right? And the initial value for a, we'll call a mass, and delta a, therefore, is the uncertainty of mass. B is density, and delta b is the uncertainty in density. So now I just plug in my values, and I find that the percent uncertainty for volume is 0.174 or 17.4%. Now, I could be done here and say my answer is 43.2 plus or minus 17.4%. But we don't always give our uncertainty in terms of percentages, right? So often we want to know the actual amount it goes up and the actual amount it could go down. We don't care about the percentage number itself. So how could we find out how much 43.2 can actually vary up or down? Well, I've got to find 17.4% of this value. So I say, hey, look, 17.4 is the percent uncertainty for volume. I could plug in the value for the volume, which we know up here, multiply on both sides, and actually find out the actual uncertainty in volume. So if I multiply the percentage by the amount of volume, I get 7.5. That means that I can list my volume in one of two ways, my answer in one of two ways. 43.2 plus or minus 17.4% here, or I could say 43.2 plus or minus the actual value. It can go up or down, which is 7.5. Now let's find the uncertainty of a number calculated with the operation of power. Remember, power is just simply multiplying the same number by itself many times. So let's say we want to find, we have a cube and each side is 4 centimeters long, and we want to find the volume. We know that the volume is one of those sides cubed, and that will be the volume. So if we want to find the volume, we take 4, we cube it, we get 64. If we want to find the uncertainty of that volume, we need to use something to figure, a rule to figure that out. Well, why don't we use the rule for multiplication, for product, since power is just multiplying it by the same thing multiple times, right? So what we'll do is we'll say the percent uncertainty for the volume is equal to the percent uncertainty of all the product parts, right? So in this case, the percent uncertainty for S plus the percent uncertainty for S plus the percent uncertainty for S, since we're just multiplying S by itself 3 times. Well, a number added to itself 3 times, or in other words, an example would be 5 plus 5 plus 5, is the same thing as 5 times 3, right? Or that number times how many times you add it. So a much simpler way to do this would be to use a rule where we say that whenever you're trying to find a quantity, so y, find this calculated quantity y where it's equal to a different quantity to a power, then the uncertainty of that calculated quantity, or sorry, the percent uncertainty of that calculated quantity should equal the percent uncertainty of the original quantity times the power. And this will be the rule for finding uncertainty whenever you're finding the power. And it really just comes from the rule for product. So if we were to take a look at that, that would be like the percent uncertainty of volume is equal to the percent uncertainty for a single side, which is 0.2 over 4, times 3, right? And so we get 15% uncertainty for our percent uncertainty for volume. Now, if we want to find percent uncertainty for the whole, or sorry, not just percent uncertainty, but the actual uncertainty, we have to find 15% of the volume itself, which is 64, which we could go ahead and do that, and it's 9.6. So we can state our answer as one of the two following. So we could say 64 plus or minus 15% is the volume, or we could say 64 plus or minus 10. Now notice, it should really actually say 9.6, but I had to write 10 because I had to round according to the rules for sig figs. If you want to learn more about that, just make sure you see some of the other videos about how to know what the uncertainty or the sig figs for an uncertainty. To find the uncertainty of a number calculated with a root, we're going to do a very similar process to that of power. Let's look at the example where we have a square that has an area of 25 square inches plus or minus a half square inch. And if we want to know what the length of one of those sides are, we're going to have to take that area and square root it, and that will be the length of one of those sides. Now, it's really important that you understand that the square root of any quantity is the exact same thing as that same quantity to the power of 1/2. This is really important to understand in general, because even if it's a cube root, you can write that same quantity to the power of 1/3, or a quad root. If this number here was 4, then you could write it to the power of 1/4. So let's quickly calculate what the length of that side is by finding the square root of the area, 25, and we get the length of the side is 5 inches. And then we've got to find the uncertainty now of that length of 5 inches. To do this, let's use the power rule, since, again, doing a square root is the same as doing it to the power of a fraction. So if we use the power rule, we say, okay, what would be the difference here? The only difference is when I'm taking a power, this n value is an integer of some kind, a whole number. And with a square root, right, we're just plugging in a half a number here. So let's rewrite this and say, okay, if y, or if a new quantity is equal to the square root or cube root or some nth root, then the uncertainty, or the percent uncertainty, will equal the percent uncertainty of the original number times that fraction, the reciprocal of the nth root. So 1 over n. And this equation is also in your pink packet that you can always use to remember. Now, let's go calculate that. So the percent uncertainty, we plug in our numbers, turns out to be 0.007 or 0.7%. Then if we want to find the actual uncertainty itself, we have to find 0.7% of 5. We do so, we get 0.03. Now that means we can write the answer in one of two ways. The length of a side is 5 plus or minus, that should say 0.7%, or 5 plus or minus 0.03. The last quantity that we have to find the uncertainty of is that of a calculated number from the operation of average. Now, I understand that average is not actually a single operation. Average is actually adding a bunch of numbers and then dividing them. However, we use this so often that we're going to come up with a unique method for finding the uncertainty in average. Now, usually what you're doing is you're measuring the same value over and over again. In this case, however, in my example here, I'm just going to have you measure a bunch of different students, and we're going to find the average height of all the students. So if we had a bunch of students and we average them, and I'm going to show these values visually. Okay, so we measured one student at 6.1, 5.3, 5.7, 4.3, and 5.6. And these were all their heights. And then we average them. We know how to do that, right? Add them up, divide by how many there are, and we get a total, an average of 5.4 feet. Now, here's what we're going to do to find the uncertainty in that. We say this is the average here, but our data all ranges around this average point. Okay, so if we want to find the uncertainty, we're going to say, hey, it really seems to have a range, like it goes so far, this far down, and it goes this far up. So what we're going to do is we're going to say the uncertainty will simply be the distance from the average itself to the point or the trial that's farthest from that average. Okay, so in this case, here it is written out in math form. So we say, look, if y is equal to an average, then the uncertainty in that is going to equal the y, again, the original average, minus the trial farthest from the average, right? These are all the different trials. So we say we take the average 5.4, and we subtract it from the trial farthest. So let's take a look. Which one's farther, 6.1 or 4.3? The difference between 5.4 and 6.1 is about 0.7. Yep, sorry, not about, is 0.7. And we look at the difference here, and we get 1.1. So this is clearly farther. So we will say that is the uncertainty, both the plus and the minus, okay? So we say the average height is calculated to be 5.4 plus or minus 1.1. Now, this is one of the methods we use for finding average. However, we also have to consider another alternative. Sometimes, sorry, well not sometimes, but all the time, all of our measured quantities that we're finding the average of, these should all also have uncertainty to them, okay? And usually we find that the uncertainty in the variation of the data, the uncertainty of this data being around the average, is much, much greater than the uncertainty of an individual trial. So we usually, after we state the uncertainty of individual trials, we usually just discount it when we talk about average and just say, hey, look, the variation really determines its uncertainty. However, every now and then, it doesn't happen too often, but every now and then, an individual trial uncertainty of an individual trial is actually greater than the uncertainty calculated by this method here. If that's the case, then we're just going to stick with the largest amount of uncertainty that we get. So if an individual trial's uncertainty is larger than this uncertainty here, then we're going to stick with that. So in other words, if my measurement of 6.1 has an uncertainty of 2 feet, right, then I'm going to stick with that. Then I'm going to just change this value to 5.4 plus or minus 2 feet instead of 1.1 as calculated here. So the rule for average is this stuff here, which is found in your pink sheet, or this statement here, which is also found in your pink sheet. So it's either one or the other, and you just pick whichever one is biggest. Now the last thing you need to do is to make sure you show any sample calculations of any calculations you made. So if you ever add two quantities, even something as simple as adding two quantities together, for example, you put two masses on something and you need to know the total mass, you have to do a sample calculation to add those to show that addition. That goes with calculating uncertainties as well. Anytime you calculate an uncertainty, you don't justify it in words like we do with measured uncertainties. You have to show a sample calculation. You don't have to show a sample for every single one, like show out the math for every single sample. You just have to show one example for each type. So if you're adding a bunch of masses many times, right, you only have to show one example. So this is what you should do. You should always make sure that you write out an original equation with variables so that they understand what it is you're doing. And then you write out, to pick one of your times that you did the calculation, you put in the numbers and you show the math with correct sig figs. And this is how you'll show your sample calculations and justify how you got that number. So it's your turn. Make sure that you look through your lab and make sure that the uncertainty for all your quantities, your calculated quantities, are calculated. So for example, in your first lab, that would be you have to find the error in sine of theta, or the uncertainty in sine of theta. Sine of theta is a division, right? So you're going to have to use the quotient rule. And then you're going to have to find the uncertainty in average acceleration if this was your first lab. If it's not, then you have to find the uncertainty of all your calculated quantities. And then make sure you write out any sample calculations for both of those, or for all of your calculations that you do.